In this chapter, we'll study properties of numerical methods, both traditional and modern. Let's see the table. These are traditional properties of numerical methods: stability, convergence and accuracy, consistency, and efficiency. They are for error control and parameter dependence of the algorithms and computational efficiency. These concepts are expanded in modern society to adaptability, interpretability, and robustness, and scalability, and energy efficiency. So we'll see some details later on. We'll first consider traditional properties of numerical methods with an example. Then the lecture will address their modern expansions with key challenges. You may try to listen to this music, the gardener's song for data-first numerical methods. I wrote two different lyrics. One is for musical, the other one is for rap. So you may try to listen to musics, and they are explaining the data-first numerical methods from two different angles, so you can understand better. Okay, let's go to the first section. Parabolic PDEs in one spatial variable, consistency. In this section, we'll introduce finite difference method for a model problem and consider the consistency. Here we have a model problem, and for parabolic equations in one-dimensional space, u sub t minus u sub xx equal f. That's the PDE, and this one is boundary condition. J is now the boundary of the domain, so it's 0 and 1. Now pictorially we can display the domain. This is spatial direction from 0 to 1. That is, we call it omega. And then now from 0 to capital T in time direction. And this equation is defined over the domain, and u value on the boundary is 0. So it is a boundary condition. And u value at time 0 is u super 0. This is initial condition. These are the boundary conditions, and this is the PDE. We'll try to solve this problem using finite difference methods. Earlier, you learned the methods and start with the partitioning and recognize unknowns on the grid points, and you collect difference equations, and then finally you have algebraic system which is called assembling. For time-dependent problem, it'll be a little bit different. However, more or less, they are the same. We'll follow the procedure step by step. Okay, we begin with the method for the differential equation by partitioning the domain. In time direction, we chop the interval into n sub t subinterval. In spatial direction, we try to get n sub x sub-intervals. Okay, so that here, for this domain, we try to make partition in time direction and now in spatial direction as well, like that. And then the first point will be x0, x1, and so on, so that there will be x and x. And now this first in time direction will be t0, super 0, t1, t2, and then there will be in general, nth level will be t super n. Of course, t super n will be here n times delta t. Okay, that's partitioning. Now, for convenience, we try to define the nth space-time slice. That means that in time direction, from tn-1 to tn in space direction whole, that means that once this level is tn, then this slice is now Sn. So time and space-time slice for Tn. So it is called the Sn. Now, we'll assume that the solutions are already obtained for k from 0 to n-1. So that assumption is here. So we assume every solution is already obtained. Now, using these known solutions, we try to get another level of solution by using finite difference technique. So in each time, we try to merge one space-time slice. That's how we try to formulate the method. Okay. The basic idea of finite difference schemes is to replace the derivatives by finite difference approximations. It can be done in various ways. We consider most common ways that are based on the Taylor's formula. Let's begin here. Now, earlier in chapter 14, you studied the approximation of second-order derivative at xi. This is the formula. It's a second-order approximation, and now this is central function value and left point function value and function value at the right point. And that is finite difference approximation. These are remainder term. We'll ignore later on these terms, so it will become error. Now, we'll use this finite difference approximation for our problem. Now, at xj and time level tn, u sub xx, second derivative, that can be, they can have this formula, difference formula, and now remainder. And Tn, nth level, so every year the function value must be evaluated at the same level. By ignoring this portion, we may try to use this one for our approximation. For convenience, we define the operator A1, that is a negative of that term, which means that this is now approximation of minus u sub xx at xj and tn. In time level is tn. So that is an approximation of this value. When t is tn, the differential equation, the original PDE equation, can be rewritten in this way. U sub t at tn, a1, u at tn equals f at tn plus this remainder. We now write these two terms into this one. Of course, here boldface u and f are vectors, and collecting the values at the grid points in spatial direction. This equation is called the semi-discrete equation, and only spatial variable is discretized and the time variable remains continuous. So we call it a semi-discrete equation. For the temporal direction, one can also apply a difference formula for the approximation of the time derivative u sub t, depending on the way of combining spatial and temporal differences. The resulting scheme can behave quite differently. Let's begin now the time discretization. This is the semi-discrete equation. Here, first we consider explicit scheme, and that is the name explicit scheme is quite you can understand why we call it explicit scheme very soon. But anyway, this is called Ford-Euler method. The reason is, in the nth space-time slice, now we focus on only two time levels. This is Tn minus 1, this is Tn. Now, in every area over there is evaluated in low level, and now the time derivative u sub t is approximated from here to there. So this is a sort of a basic level, and then time derivative is made along with that difference from Tn, and so that now from Tn minus 1 to Tn, this difference is used. Because everything is on this level, this time derivative is a kind of a Ford scheme. So we call it the Ford-Euler method. And so this is the Ford approximation. By ignoring this portion, now V value is approximation as U, so we can write in this way in detail. This is the approximation, and now we write down this one in detail pointwisely, and here trace component is here. This is the Ford-Euler, because now our main time level is Tn minus 1. Okay, and this scheme can be rewritten as this one. First multiply delta t and delta t over delta x squared. Now we are using mu notation. Mu is delta t over delta x squared. Then here, along with a little bit of algebraic manipulation, you can reach this equation. So you can see now, assuming these values are known, and you can get it quite easily, explicitly. So that is called explicit scheme. Also in time approximation is a kind of Ford, so that we call it, and also the Ford-Euler method. Okay. Now we define error. Now EJN is here true value at xj and tn. Now that is approximate value obtained by using this equation. Then here, okay, now if you subtract from here to there, then rather than u and v, you can replace this portion in e, and then you have that portion, error, remainder. So that is exactly, this is the error equation. And from two equations, we can get this one quite easily. Now we begin with the concept of consistency for the numerical procedure in this equation. Okay. Consistency. A simple requirement for an accurate numerical method is that the discretization becomes exact as the grid spacing tends 0, which is the key concept of consistency. Let's see the formal definition. Given PDE, PU equal F. In our case right now, PU is the same as, okay, P can be written in this way, that there is T derivative minus now X second derivative and U. So the P itself is this operator. Okay. And then finite difference came, and our approximation along with V. And the finite difference scheme is said to be consistent with the PDE if for every smooth function, PF, P phi minus P, the finite difference operator, phi, and converges to 0 as the grid spacing, grid size approaches 0. That's the definition of consistency. Not all numerical methods based on Taylor series expansions are consistent. Sometimes we may have to restrict the manner in which delta x, delta t approaches 0 in order for the numerical method to be consistent. And that equation means that for delta x, delta t, they are approaching 0 and independently, so that it's converging to 0, it's converging 0. Probably one can go to 0 faster and the other one slower. In any way, they are approaching 0, then here this should approach 0 without any restriction. Then we say the finite difference method is consistent. Here, let's see the Ford-Euler method. And for the method, here P is this one. Now the Ford-Euler scheme is made in this way. Okay, so here now phi sub t is this one, and there is a Ford approximation, and these are remainder. And for x second derivative, we have second order approximation, and these are remainder. This subtraction will make p phi, and this subtraction will make that finite difference operator applied on phi, so that, and by subtracting, we can get this portion, and we can get that portion, and move this one left hand side, and this whole thing is the remainder. Okay, here we have the equation. Now after subtracting, we move this onto the other side, and we have that. But these are approaching 0 in as delta x and delta t converges to 0. So arbitrarily and independently, delta t, delta x goes to 0, and then now this term will approach 0. So the conclusion is the Ford-Euler method is consistent. Okay, so it passes one step. And here we define truncation error. Once for given solution PU and its numerical approximation, then you have some remainder for this portion, and we call it the truncation error. And now the consistency is saying that the truncation error approaches 0 as the grid parameter approaches 0. So this one is the truncation error approaches 0 as the grid is defined. And so the consistency is related with the truncation error. for the Euler method, we can see easily from this analysis that is order of delta t and order of delta x squared. So we can say in this way, for the Euler method, the truncation error is order of delta t and order of delta x squared, and is converging to 0 as the grid size approaches 0. Okay, to understand the consistency better, let's see this one in pizza delivery. And while a pizza box is delivered to the correct address, that is consistency. It doesn't guarantee that pizza inside is the one ordered. And this introduces the concept of accuracy. In a sense, the consistency is looks done well. Then that is a kind of consistency. But a real the pizza is not guaranteed, even though a pizza box is delivered to the correct address. So this inside the pizza inside may not be different, then the accuracy is broken. In business, consistency refers to the sustained and reliable adherence to a set of standards, strategies, or practices. In a human relationship, consistency refers to a predictable and dependable behavior that builds trust and security. People are using the consistency in this sense. Okay, that's the end of section. Thank you.